In this screencast, we're going to look at a few different reaction types. The first type that we're going to start off and look at is a combination reaction. Now, there are a lot of synonyms for some of these reaction types, and so I want you to be able to recognize both. Sometimes these are called combination reactions, and sometimes they're called synthesis reactions. And basically, in this reaction type, this is the joining of two or more elements or compounds to produce a product. So let's look at this image, and I like this image for a few reasons. One is it shows you what you physically see. And what we see here is this is a magnesium ribbon, so it's magnesium solid, and it's burning in air, and it gives off a really bright light. This is the same thing that a lot of times you see in sparklers, right, in the 4th of July. And then you're left with this oxide. And so now we can look at the molecular level. And so we can see, look, we have magnesium metal, and you can see how the metals sit here in a lattice. And then we have oxygen atoms. They are in the air. There's a lot of space between them. And then they come in contact with the metal as it burns and forms this metal oxide. Now, what I want you to notice when we write this is here's the chemical equation. And we have magnesium solid reacting with oxygen. And notice oxygen's diatomic. So that's that oxygen in the air that's diatomic. And then it produces the magnesium oxide here. We have two or more things here going to produce a product. So basically you see generally you see two things going to one thing. But basically what you're looking for is fewer products. Okay, so let's look at another example. When you have calcium solid reacting with Cl2, which is chlorine, notice that's another diatomic atom that forms calcium chloride. That's another example of a combination or synthesis. We've got two products, it goes to one reactant. Then we have magnesium oxide reacting with CO2 gas, and it goes to magnesium carbonate as a solid. The second type of reaction we're going to look at can almost be viewed as the opposite of this. It's a decomposition reaction. And in this reaction type, right, you produce two or more products from a single reactant, right? So you see this in an airbag. The airbag is filled with sodium azide, which is NaN3. And what happens is upon impact, that sodium azide will decompose into sodium, and I want this to be balanced, and nitrogen gas. And it's the nitrogen gas that fills up the airbag. This is an example of a decomposition reaction. You have one reactant and it goes to two or more products. And that's how we recognize that this is a decomposition reaction. Another example of a decomposition reaction is calcium carbonate. That's a solid. And when you heat calcium carbonate, it decomposes into calcium oxide, which is a solid, and carbon dioxide gas. Now, I want to point out another type of decomposition reaction that you can see, and this happens with hydrates. So I want to talk to you about what a hydrate is. When we talk about a hydrate, this is a complex with water. So for example, you see copper sulfate, and that's the ionic complex, but then it has a fixed amount of water that goes with it. This is represented by a dot and then a coefficient 5H2O. That means in this kind of structure with copper sulfate, there are 5 water molecules associated with it. This is considered to be one reactant, right? So that's the hydrate. And so when it goes through a decomposition reaction, it'll break apart into copper sulfate. And to do this, you heat it. And water. And so I want you to be aware of what a hydrate is. So if you see a dot in the middle, you're not surprised. Another type of reaction that we see is a single replacement reaction. These are also known as single displacement reactions. You can see them like either way. And basically what happens here is you have a single reactant and then you have some sort of binary compound. Binary just means there's two, right? And so this would be, for example, an ionic compound or a covalent compound, but two things bonded together. And then what happens is A comes in and replaces B here. And so I kind of view this as a dance where the chemical compounds are dancing here and somebody cuts in and replaces one of the chemical elements there. So hopefully that helps. Let's look at this. So for example, if we have zinc solid plus copper sulfate, right? And this is a single replacement reaction. It's important to understand that the metal will replace another metal, right? So if a metal is the single thing that's by itself, it's going to replace the metal. We're not going to see two metals come together, right? They both have positive charges. That's not going to happen here. So when we look at this, right, to predict this product, we say, hey, look, here is zinc, and it's going to come in and it's going to replace the copper and copper sulfate. And so that means that copper is going to be by itself. And then you need to predict the product here. And so to predict the product, what you'll do is you'll say, hey, look, I know that zinc has a +2 charge from my periodic table. And I know that sulfate has a -2 charge because I memorized my polyatomic ions like Dr. Pierce told me. And then I'm going to crisscross applesauce this sucker down. And now I have zinc sulfate. All right. If there's a nonmetal replacement, a nonmetal will replace another non-metal, right? So that's what you're going to see with single replacement reactions. Now, you can also have double displacement or replacement or double displacement. Reactions. And I kind of view this as like a square dance, right? Where you have two partners here and two partners here and the partners change. And so now you have a different pairing here. We can see this with letters. Again, right, the metal or the cation in the instance of if you're using NH4+, right, will replace the metal or the cation, right? And so here's the thing you can do. You keep the non-metals there, which are the second thing, or the polyatomic ions. You keep them there. And then the only thing you do is you switch this guy and this guy, okay? So you just switch the first things that come along. So let's look at an example of that. We've got barium chloride reacting with potassium sulfate. And we want to predict the products of a double displacement reaction. So when we come here, we say, okay, hey, look, my first product, what I'm going to do is I'm going to keep the chlorine and the sulfate there. And I'm just going to switch the barium and potassium. But here's the deal. We know these have different charges. So we have to look at these as the ions that they are. So when we do this, we come here and we say, hey, look, barium, and I'm going to do this up here. Barium has a +2 charge, right? And it's going to take the place of potassium. So it's going to form a new bond with sulfate, which has a -2 charge. We crisscross those down, right? And now we get barium sulfate. And so we're going to come down here and write barium sulfate. We're going to talk in a later screencast about how we would recognize if this was solid or aqueous, but we're not going to do that right this second. Now, we do the same thing for potassium. We say, okay, potassium now is going to switch places with barium, and potassium is going to form a complex with chlorine. Now, I want you to notice here, chlorine, when it's an ion, is chlorine minus, right? When it's a gas, it's Cl2 gas, okay? So it's diatomic when it's a gas, but when it's an ion, it's all by itself because it's in water, it's in an aqueous solution. So we're going to crisscross these guys down and say, great, we have formed potassium chloride. Now, the next thing you need to do is you need to check and see if it's balanced. And if it's not, then you need to balance it. Sometimes, and you can make a list if you want, but sometimes you can balance by inspection. And you can say, look, there's one barium here. There's one sulfate here. Those are balanced. There's 2 chlorines and 2 potassiums. And it's right, there's just potassium chloride, so we can put a 2 right there. Okay. And we'll practice this more. Now, let's talk about the last type of reaction in screencast, which is combustion reactions. Now, combustion reactions produce heat and almost always react with oxygen and another element or compound. What you're going to see here is sometimes you can have combustion reactions with things like sulfide, okay? But most often what we are going to be interested in is the combustion of hydrocarbons. I want to remind you, hydrocarbons are molecules composed of carbon and hydrogen, and they react with oxygen every time you see a combustion, and every time they're going to produce CO2 and water, each time. Now, when we look at this, it's important to see that this is not balanced. And so I'm going to go ahead and kind of make a list of my atoms here. I have 1 carbon, 4 hydrogen, and 2 oxygen. And then over here I have 1 carbon, 2 hydrogen, and 3 oxygen. And the carbons are balanced, so I'm not going to mess with them right out of the gate. Instead, I'm going to look and see if I can change my amount of water to get the hydrogens to balance. So I'm going to put a 2 here. When I do that, that makes that 4, and that's correct. And then I'm going to see if the oxygens just kind of fall out as being balanced. When I put a 2 there, it makes this 4. So it doesn't fall out, but it does make it easy to come over here and balance the oxygen here with a 2. And now we have a 4 there. I want to do one more practice of balancing combustion reactions and then talk to you about a trick. So we're going to balance this combustion reaction. When we look at this reaction, what we see here is on this side we have 3 carbons, 8 hydrogens, and 2 oxygens. And then on this side we have 1 carbon, 2 hydrogens, and 3 oxygens. Now, again, I want to leave the oxygen to last because it's in 2 compounds in the products. It's CO2 and H2O. And so I'm going to leave carbon and hydrogen till the end. So I'm going to start with, I said carbon and hydrogen till the end, hydrogen and oxygen till the end. And I'm going to start with carbon. And so I come here and I say I have 3 carbons. And I want to make this 3 carbons as well. So I'm going to do a 3 here. Okay. When I put a 3 there, I need to see how that affects my oxygen numbers. And so 3 times 2 is 6 plus 1. And so now that is 7 here. So my carbons are balanced. The next thing I'm going to do is go to my hydrogens. Again, I'm leaving oxygen alone because it's in so many things in the product. And when I come here to look at my hydrogens, I say, okay, hey, there's water. And I can make this 4H2O, and now that gives me 8. And my carbons and hydrogens are balanced. And so now let's deal with oxygen. 3 times 2 is 6. And so when I'm looking at that, I'm saying 3 times 2 is 6, plus 4 is 10. And so if I come over here to oxygen and say, great, let's see that with orange, there are 5 O2. Now I have 10, and you can see that it's balanced. I want you to notice that both of the examples we've done have an odd number of carbons in the hydrocarbon. When you have an even number of carbons in the hydrocarbon, it is going to make it easier to balance if you just double the hydrocarbon first. Right? And so, what do I mean by that? If you have C4H10 plus 13, plus O2 goes to CO2 and water, right? It will make it easier for you to balance if just out of the gate you put a 2 there. And then calculate it, but only do it if the carbons, if there's an even number of carbons. If there's an odd number of carbons, that's not helpful, right? So when we look and do this, we say, okay, great. That means I've got 8 carbons, 20 hydrogens, and 2 oxygens, okay? And then over here I have 1 carbon, 2 hydrogens, and 3 oxygens. And so now you can balance the CO2, and you can put an 8 here, and that makes that 8. And then 8 times 2 is 16, plus 1 from the water, that makes that 17 now. And so we can balance the hydrogens by coming over here and saying, okay, there's 2, but I really need 20. So that would become 10 H2O. And so now I have 20. And that changes my oxygens. So now I have 16 plus 10, that's 26 oxygens. And so those are balanced. And then I'm going to come over to my oxygens and say, okay, if I've done that, I've got 26 there, I can make this 13. And now I have 26 oxygens on that side, okay? So you do get into some big balancing numbers, and I wanted to show you that so when you saw it, you weren't scared or surprised by kind of these large numbers. The other thing I want you to be aware of is sometimes with combustion reactions, they show these as fractions. So you always want, the kind of rule is you always want these numbers to be in the largest whole number. So if for some reason it gets doubled, you would divide by 2 to get them in the largest whole number. But with combustion reactions, sometimes historically, they've been shown as fractions. It's the only time that I've really seen this. And I don't care which one you do if I were to ask you to balance this. I don't really care which one you do, but I do want you to be able to recognize both, okay? And so either would be correct. Just want you to recognize that. All right, we will continue to practice these. And as always, if you have any questions, please feel free to pop by my office.